Here are the solutions to the worksheet that we started. Problem 1 part B and problem 2. So we worked hard to learn how to combine together torque net equals I alpha and F net equals ma with a consistent positive direction to figure out what the angular acceleration of this disk is. And now B asks, if the mass is released from rest, how long does it take for the mass to fall 1.5 meters? So if we release it from rest, how much time do we have to wait before it goes down a distance of 1.5 meters? That sounds like a kinematics calculation, and this thing is just accelerating linearly. So if I could figure out what its acceleration is, well, I know what alpha is, and here's the relationship between the y acceleration of this and alpha of the disk. Ay equals r alpha. So the first thing we're going to do is calculate Ay from that relationship. And when we put those two things together, we get 3.267 meters per second squared in the downward direction is the acceleration of this block. And then from there on out, it's a kinematics calculation. We want to know the time. It's released from rest, so Vy0 is 0, and Ay is that positive number we just found out. And what we want to know is, what is t when y minus y0 has a certain value? So y minus y0 is 1.5. The acceleration is given there, and in that case we can just solve for what t is, how long it takes to get to that final y of 1.5 meters. And that's 0.958 seconds. That's part B of problem 1. Now on to problem 2, where we've got a rod of length 1 meter, mass 2 kilograms, pivoted at one end in a vertical plane. We want to find if it's released from rest at the dashed position, what's its angular acceleration? In other words, it's speeding up, speeding up, speeding up. What's its angular acceleration when it's 30 degrees below the horizontal as it passes that point? To do that, well, what's causing it to angularly accelerate? Gravity. Gravity is being applied at all points along the rod, but I can use that simplifying assumption that if we're calculating the torque due to gravity on an extended object, we can just pretend that the full force of gravity for the full mass of the object is concentrated at the center of mass of the object. And anytime we have a symmetric object, the center of mass is always at the center of symmetry of the object, and here for a meter stick that's exactly in the middle of it, so it's halfway down the meter stick. So we're going to say at this instant in time where it's 30 degrees below the horizontal, the weight force due to gravity on all the bits of mass is as if it's being applied, the full weight force is just being applied at the center of mass. And of course it goes straight down, as always. So if I want to calculate the torque in this case, we could talk about the signs of it, but if I take the clockwise direction to be positive, this would be generating positive torque. To calculate that torque, one way to do it is just to find the moment arm for that force. So I draw the line that contains the force and look for that shortest perpendicular distance to the axis, mg, the force magnitude, times r perpendicular, and r perpendicular is just 0.5 times the cosine of 30 degrees. That's 0.433 meters. You can see up from the calculation there. So mg times 0.433, that works out to 8.487 Newton meters. Then, once I've found the gravitational torque, it's the net torque on the object. There's no other forces exerting torques on it. And therefore, that net torque, which is just the gravitational torque, is equal to I times alpha. And if I put in the moment of inertia for a rod pivoted about one end, I believe that's 1/3 ml squared. Here it is in our table there. Rod pivoted about an axis at one end is 1/3 ml squared, where L is the length of it and m is its total mass. Therefore, when I solve for alpha, I get the gravitational torque divided by I is 1/3 ml squared. And putting that all together, I get an angular acceleration of 12.73 radians per second squared. Now, one thing to notice is where that angle theta came into here. It came into this 0.433 meters. That involved the cosine of 30 degrees. Notice at smaller angles that cosine would have been a larger number. So the gravitational torque is largest when it's up here. In other words, it's angularly accelerating a lot when it's horizontal. It's angularly accelerating less when it's down here because I have a cosine of 30 degrees instead of cosine of 0. When it's down at 60 degrees in this direction, its angular acceleration is even less. And when it's down vertical, as it's zooming by that bottom position, when it's hanging vertically momentarily, its angular acceleration is 0. So the torque, gravitational torque, is big, smaller, smaller, 0, and then the torque starts to switch direction. Then gravity, once the bar has rotated over in this direction, gravity is trying to twist it in the opposite direction. So the torque would change sign there, and so the angular acceleration would switch directions as well. All right, that's problem 2. So we're going to talk about some other simplifying things that are associated with the center of mass. Here's what we found out and just displayed a different way. If I've got an unusual shape object which is pivoted to rotate about a fixed axis, if we can figure out where the center of mass is and what its coordinates are in a certain coordinate system, then the simplifying principle is that when we're calculating the gravitational torque on that extended body, we can pretend that the full force is just one force being applied at the center of mass and use the corresponding moment arm, or however you're going to calculate the torque with that, just pretending there's only one force acting. There's a similar simplification that we can use when we're talking about gravitational potential energy. In other words, if we have an object, so here's an unusual shaped object, and it's pivoted to rotate about this particular axis right here, and as if we let gravity act and we assume most of the mass is over here on this side, gravity is going to try to rotate it down along this direction, so it might fall. And we want to say that its potential energy is changing, but unfortunately, if we look at little bits of mass on there, those masses are going to move downward by different amounts. So what I've done is just rotate that object, which I've drawn as gray up here, in a rotated location where it's rotating about this fixed axis, and drawn it in kind of a pink color. M2 goes from here, it's sort of out on this lower bump there, to this location. M1 goes from this location on the gray to this location on the pink, and they've gone down in the y direction by different amounts here. But let's undaunted, let's calculate the change in potential energy of this entire object. If we think of dividing it up into lots of little bits of masses, M1 and M2 are just a few of them. The change in potential energy is going to be, well, it's the change of potential energy of M1. That's going to be M1 times G times the change in Y1, plus the same thing for Y2. M2 is going down by a different amount, and I've got to do that for all the little bits that comprise this object. Ones that are close to the axis are hardly going to move down at all. Ones that are far from the axis might move down quite a bit in that rotation. So the upshot is the change in potential energy, well, I can rework that into a different form. There's a common factor of G in all these terms, so I'm going to factor that out on the right-hand side, and then look at what's in parentheses here and try to interpret it. M times the change in Y1 plus M2 times the change in Y2, adding those up is almost the same thing as the change in the y-coordinate of the center of mass. So if I simply multiply by the total mass of the object and divide by the total mass of the object, what's on the right-hand side here in this ratio is the change in the y-coordinate of the center of mass. And so the change in potential energy is the total mass times g, the total weight of the object, times the change in the y-coordinate center of mass. And we can visualize that by saying, oh, let's imagine the center of mass is here, somewhere partway out this big point there. And here it is after rotating. This is the change in the y-coordinate of the center of mass. If we can figure out what that is, it's easy to calculate the potential energy change in this point to this point. The object has gone down, so it's reduced the potential energy stored between that object and the Earth, that system, and the change in potential energy, instead of looking at all the complicated little bits of mass that are moving down by different amounts, we can simplify our life by just looking at how far down the center of mass moves when we calculate the potential energy. So that's another convenient way to use the center of mass. Here's another simplifying way to think about things. What about the kinetic energy of the object? We're going to, I'm using this because we're going to start using energy methods with rotating extended objects. And if I'm worried about the kinetic energy of the object, if the object rotates about a fixed axis, then the kinetic energy of this object would be the sum of all the 1/2 mv squareds for all the little bits of mass. Now that's complicated because m1 is moving at a smaller speed than m2 at any given time, and a different mass that's very close to the axis will hardly be moving at all, whereas one that's far out might be moving really fast. We have all these different 1/2 mv squareds. We've got to add them all together to get the total kinetic energy of the object. But we can simplify that a little bit by replacing V1 with R1 omega, V2 with R2 omega. That's our relationship between linear and angular quantities. And then squaring out each of those terms that's in parentheses, that gives me an R2 squared omega squared. And then factoring out everything here that doesn't depend on the 1s and the 2s and the 3s, the different bits of mass. So there's a 1/2 I can factor out on the left. There's an omega squared because there's only one omega for the whole object at any given time. So all those omegas are the same. Let's factor that omega squared out on the right-hand side. And what's left in the middle is, by definition, the moment of inertia of the object. So what that means is that if I want to know, if I know how fast this thing is rotating, it has angular velocity omega at a certain time, and I want to calculate its kinetic energy, I don't have to bother adding up the 1/2 mv squareds for all little bit of mass. All I can do is figure out what the angular velocity of the full object is and calculate 1/2 I omega squared. And notice again, this is just like the linear formula. This I is the analogy to an m. This omega is analogous to v. So this is just like 1/2 mv squared written in angular coordinates. That makes it easy to remember. So there's our simplified formula for the kinetic energy in angular coordinates. So that's for an object rotating about a fixed axis. Those are some simplifying things that we can use. Rather than adding a bunch of stuff up, we can just calculate one item and simplify our life. Here's another case which is elaborated in the book. I don't think I have a justification of it here. But here's a more complicated situation. This situation up above here is for an object rotating about a fixed axis. Here we're concerned with an object that's rotating about its center of mass. So it's like a wheel that's rolling on the ground, or a ball that's rolling on the ground, or an object that's rotating about its center of mass as it translates through space. So if the object rotates about its center of mass and it has an angular speed omega at some instant of time, and the center of mass is translating through space at a speed v center of mass, then its kinetic energy can be written as a sum of two terms, right? It's not just rotating about the center of mass, but it also has some additional kinetic energy by virtue of the fact that the whole thing is flying through space. And you can justify, I'm not going to show it here, that you can write this as a sum of two terms. One is just the kinetic energy due to rotating, the rotational kinetic energy about the center of mass. So what's its moment of inertia about the center of mass times omega about the center of mass, plus 1/2 times the total mass times the speed at which the point about which it's rotating. We would usually call that the axle, but in this case, it has to be the end center of mass for this to work. So we have translational kinetic energy and rotational kinetic energy are kind of combined together in this case, where the axis isn't fixed, but the axis is rotating through space. So we're going to use this to analyze wheels and balls and whatnot. So, for example, here is a wheel rotating along the ground. I've painted a red stripe on it, so the red stripe is going to go around and here it's gone one complete revolution. There's an axle, and it's moving with speed v center of mass. In cases where, in order to analyze how objects move down a plane when they roll without slipping, in other words, we could imagine rolling a ball down an inclined plane. It doesn't slip at all, and so in those cases, we want to say something about the work done on a system which consists of this rotating disk by the frictional force. And this is confusing, but it comes from the fact that whenever we would calculate the work done by a force on an object from the point of view of a certain observer, we look at how far the point of application of that force moves while the object is undergoing whatever motion it has. And in this case, if we've got an object, here I'm imagining a ball rolling down an inclined plane, as it rotates, for example, at the instant shown here, this point on the edge of the ball is actually moving up, right? It has lifted off the plane and it's moving upward. This point, which is a little bit ahead of the point of contact, is actually moving down at this instant. This point right in the middle, which is where the static friction force is acting, is neither moving up nor moving down. So the static friction force between the rolling ball and the plane is being applied, of course, in the direction up the plane. If it weren't being applied in the direction up the plane, the object wouldn't start rotating at all. So if it's rotating without slipping, there's got to be a static friction force. It's pushing up the plane, but the important thing is that the point of application of that friction force is not moving, and therefore the friction force does no work on the object as the object rotates down the plane. So, for example, we can now analyze things like a system. If we can take our system, if we got a ball rolling down an inclined plane, what's causing it to go down the inclined plane? Well, it's the gravitational force, and we can take our system to be the rolling ball plus Earth. We'll take gravity to be an internal force, but let's take the friction and normal forces, which are also both acting on parts of the moving system, external. The normal force, of course, does zero work. We're already used to that because it's, any motion that we can see, it's in the direction perpendicular. But now we're actually finding out here that the friction force also does zero work. So if we write down a relationship, the net work done by external force is equal to delta Ke plus delta Pe, the net work done by external forces is actually zero in that particular situation. Let's keep that in mind as we do the next worksheet, which starts with problem 1, where we've got a ball of uniform density, and it's released at rest from the top of a 4-meter long plane inclined at 20 degrees to the horizontal, and we want to know the speed of the ball's center of mass after traveling the 4-meter distance as measured along the plane. And we're going to use that same principle I just wrote down. Net work done by external forces is equal to delta Ke plus delta Pe, and the left-hand side is going to be 0 if we choose our system to be the ball plus the plane, with gravity being an internal force. Okay, so it rolls without slipping down the plane. We'll be back with solutions to that and the later other parts of the problem and finish up the chapter when I come back.